Okay, ladies and gentlemen, I'm going to give myself this morning for 0B about a C minus on instruction. So we're going to up this up to at least hopefully a B today, at least. Okay. I'm going to preface 12.3 as something of, I don't want to say non-importance, but there is not a lot on the AP exam. Many years I didn't even teach this lesson. Many years. Next year, it's not even part of the curriculum. So I don't know if they're going to phase it out this year or emphasize it this year. That kind of makes sense. So I'm going to teach it. I'm going to tell you what you guys need to know. I really believe this is a whole lot more review from chapter 3 bivariate data. Okay? Bivariate data, I believe. It's more of that than it is teaching inference for slopes. Okay? So you can notice from your sheet there's not a whole lot of notes there. I think, like I said, I think I really messed up first hour today in giving maybe too much information. Let's talk about it. Maybe I'll do better. Inference for slopes, confidence intervals, and hypotheses testing. So this has both confidence intervals and hypotheses testing. Okay? All right, here we go. We're going back, like I said, a lot of it to chapter 3. Chapter 3, we had y-intercepts, we had slopes, we had x values, y hat values, we had r squared, s, residuals. You'll kind of think about all that stuff, yes? Definitions of each one of those, interpretations of each one of those. We had a lot going on in that chapter. That chapter has a lot of interpretations that we don't use, but just that one chapter. And here they're coming back. Okay? Scatter plots, duration intervals between the eruptions of Old Faithful, of all. Y'all, okay, just kind of, as long as you can, all 263 eruptions. So that is the population. Fair enough with what I've done? Again, just soak this up. No, you don't have to know this, but I think it's good information, if that kind of makes sense what I'm saying. Okay? The population least squares regression line is shown in blue. So there's a bunch of eruptions right here that were the duration of about 2 minutes. There were a bunch of eruptions over here around 4.5 minutes. There were a couple in between, but there is 2 big clusters. We have that least squares regression line, the line of best fit. Okay? We know that the line of best fit is some y hat is equal to some value x plus some value, right? This being the slope and this being the y-intercept. And of course, the y hat is the interval until the next, and x is the duration time. Again, just soak all that stuff up. That's chapter 3 stuff, right? You have the distance from here to here, which is the residual. That's a negative residual. The distance from here to here is also a residual. That's the positive residual. Remember, residuals are A minus P, AP, actual minus predicted. The sum of all the residuals should be 0. The square of all the residuals is part of this least squares regression line. Okay, so we have a sample regression line as y hat is equal to a plus bx. That's what we did all in chapter 3. We used samples. We didn't really realize it at the time, but that was pretty much one sample. Okay. Y is the estimated value of the y. A is the sample y-intercept. B is the sample slope. Again, just stuff we kind of know already. We also have population lines, which of course we never do populations because if we know the population, we don't know anything, we don't need to know anything. But they're going to use alpha and beta. And so we got a little bit of confusion because I have alpha, and you guys are used to seeing alpha as the significance level. In this particular case, alpha is the y-intercept for the population. This is the slope for the population. Just kind of bear along with that. Yeah, go with it. Boom, 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 boom. Here I took a sample of eruptions from Yellowstone or from whatever that thing was, Old Faithful. And I found the least squares regression line. It's different than the blue one, which we know that samples differ from sample to sample, and they also differ from the population because of sampling variability. If I took another sample, then I got another line. If I took another sample, I got another line, and none of those are the same as the blue line. Good enough, kind of good with all that stuff, yes? Notice that the slopes of the sample regression lines vary quite a bit from the slope of the population. We had 10, we had 12.5, we had 15, and we had the population of 13. The pattern of the variation in the sample slopes is described as the sampling distribution. If I did this over and over and over and over and over and over again, eventually I'm going to have the sampling distribution of all the slopes. That is a distribution of samples, not the sampling distribution, but we still get the idea. Fair enough with all that stuff? Notice that it's approximately normal. Notice that the height of that is pretty much the same as the populations. As the sample size increases, that's going to decrease all that stuff, soak all that stuff up. Again, it's just stuff that you already know has really nothing to do with this, and yeah, don't worry about that. Yeah. Don't worry about this. Yeah. I'm going to say it really quickly just because you have a homework question over it. The conditions for inference for slopes are different than all your other conditions. The data needs to be linear. The data needs to be linear. It needs to look linear, right? We'll look at the scatter plot and just say, you know what, it looks linear, we'll go with it. If it doesn't look linear, we're not going to do it. Which doesn't, I mean, that makes a whole lot of sense, right? I would be okay doing the inference for this. I would not be okay doing the inference for that over there because that doesn't even look linear. I don't think inference is going to help me any at all. Good enough with that? So it's got to look linear. It's got to look linear. We need the 10% rule. We need the 10% rule still. So that's still good. Got to have the 10%. The samples need to be less than 10% of the population. That's what the independent one says. Okay? The independent one is the 10%. It's the, I've never called it independent, but the reason why we call it independent now is because it helps my saying. Normal. The residuals need to be normal. A box plot of the residuals need to be non-skewed, non-outliers. Non-skewed, non-outliers. Again, I'm just saying this just in case. I have not seen it on an AP test in forever. It's not on my test. It's on your homework. The conditions. Residuals need to be normal. We need equal standard deviations about the line on the residuals. The residuals need to be equidistant from the line. This is a good one. All these residuals are pretty close, scattered. This one's bad. They start off fairly small residuals and they end up very large residuals. So we need equidistant residuals from the line. Equal, about, again, about. Variability of the residuals in the vertical direction should be roughly the same. The residuals should be roughly the same throughout. Okay? And then the last one is randomness. So the randomness and the 10% are still there. It doesn't have a large count. It doesn't have a large count. The data needs to look linear. We need the 10% independent. We need the residuals to look normal. We need equidistance of the residuals. And we need randomness. Homework questions. No test questions. I don't think there's going to be an AP question. But if there is, you're better off than 85% of them because a lot of teachers don't even go over that. I don't think you're going to need it, is why they don't go over it. Fair enough? Any questions about that? L-I-N-E-R. Liner. That helps. That helps. Randomness, 10%. It needs to look linear. And then the residuals need to be normally distributed, and the residuals need to have equal variability. Okay, take that for what it's worth. Homework, non-test. Yay, click. Random. Miss Barrett's class, they dropped 70 helicopters in random order. Check whether the conditions are met. They're going to typically give you this information. The data looks linear. This is different because you're used to seeing scatter plots, but they dropped helicopters from 150 feet. They dropped them from 200 feet. They dropped them from 250. They dropped them from 300. Say again? Centimeters. Sorry, thank you. That would be really high. And then 450. And then they saw how long it was in the air. So that's why they're all vertical lines. Fair enough? It looks linear. So we fit the L. We had a random selection. It said that in the deal. 70 is less than 10% of all helicopter drops. How do I know? Because I can drop infinity. The scatter plot or the residual plot looks roughly equidistance variability. There's the residual plot that looks normal. Y'all okay with all that stuff? You're going to have a homework question. It's going to talk about it, but they're going to give you that. And you're going to say yes or no, good, bad, whatever. Click. Don't overreact to minor issues on a graph. Kind of like we didn't with the normality with my low numbers. We didn't overreact to strong skewness outliers. Okay, done with that. Done with that. A will estimate alpha. That makes sense. B will estimate beta. That makes sense. S will estimate sigma. We've known that since day 2. You don't need to know that. Click. Y'all remember seeing one of these? You gotta know this thing big time for unit 3. Actually, it's unit 2 up there. Unit 3 or chapter 3 in our book. You guys got to remember. So I got a lot of stuff for us to practice on this, right? We have our predictor. We have a constant and a drop height. And your constant over here says coef. That's your y-intercept. The coef for the drop height is the slope. Okay, that is the slope. We remember that we have S right here. That is the standard deviation of the residuals. We talked about that in chapter 3. Okay, and then we talked about R squared. That is the percent of variability in Y. I know you probably don't remember that, but again, this is more review of chapter 3 than it is 12.3. You also remember that we had R. We would take the square root of that to get R. R tells us the strength and direction of a linear relationship. R squared tells us the percent of variability. We never used this for anything. And then we used to not use rest of this stuff. Till today. Till today. Because now this is the standard error. The standard error. We have the standard error of the y-intercept, and we have the standard error of the slope. We typically don't do anything with the y-intercept because that doesn't tell us much of anything. We typically look at slopes. Here is the t critical value. I'm sorry. It's the t-test statistic, which is different than the critical value. That is the t-test statistic. And then here is the p-value. that goes with that t statistic. Okay, with t being 28, p-value is really, really, really small. Okay, so that stuff, now we learned at least what this is. Okay, beautiful. What is the estimate for alpha? That is the y-intercept, which is that one. What is the estimate for beta? That is the slope. Again, we need to know that stuff. What is the estimate for sigma? And that is this number right here. And then the estimate of the slope, which is this one right here. Again, we'll kind of, I got you a worksheet today. We'll kind of go through that, a little bit of it, and then let you guys finish it out. Okay? Here's my A value. Here's my B value. There's my S value. And there's the standard error of beta. Standard error of the slope. Again, all we focus in on is the slope. Okay. So now let's talk about confidence intervals for slope. Confidence intervals for slope. Okay. Same formula that you guys have used for all confidence intervals. You got a statistic. Well, our statistic is going to be B. It's going to be our slope. Our slope from our sample is not beta, it's sample. Plus or minus. Because we're dealing with means, it's still a t. Now, this is the point where I got to make sure you guys understand, and I had a big discussion with 0 Hour about this because they asked a great question. This t right here is the critical value. That is the test statistic. Those are different, right? They are different. Just like when we did confidence intervals, right? For proportions, we said it's p hat plus or minus z square root p 1 minus p over n. And then we did hypotheses testing, which was z is equal to p hat minus p over the same square root of p 1 minus p over n. These were hats. Those are not the same. That is the critical value. That is the z-score for 99, 95, 90, whatever level they tell me is what that is. This is the calculated for how far this value is from here. Right? They're completely different. And I think that's why they put the asterisk here, to make sure you understand that those are not the same. Yes, no, somewhat, maybe. I know it takes a little bit to think, well, wait a second, they gave me the t. No, they didn't. You're going to turn this one into a p-value. That one you're not. That one's telling you how many standard deviations away we're going to be. We're going to go for 95 or 99 or 90 or whatever it is. And then we got some weird, but all you really need to know is this is SE sub B. Okay? That's the SE sub B. They will give these to you as a table. It's your job just to get the information from the table. Okay? Click. There it is in non-hieroglyphics. There's that B. There's the T. Yeah, I don't see, it's not. Oh, there it is. There it is. There it is. Here it is. This is huge. This is where your DF is n minus 2. And if you guys can think back when you had that nice little program that Coach Mayer wrote and you did critical value for means, and then it said DF and it said n minus 1 for means and n minus 2 for slopes. So the DF is different, okay? And if there's an AP question, that's what it deals with. Finding the critical value. Finding the critical value. Which you know how to do already. It's just you got to know that the DF is n minus 2, not n minus 1. The values of t given in the computer regression output are not for the critical values for a confidence interval. Oh, that's what that says. The values of the t given in the computer regression output are not the critical values. They're a different t. Those are the test statistics. Okay. We did this in that chapter 3, right, where we had those Ford F-150 trucks, Super Duty crew cabs, and they had so many miles on them, and we figured out how much the price was, right? And we plotted all those X's and all those Y's. Yay. And we found the least squares regression line. As the more miles went up, the price went down. Here's a visual of the the residuals. There's a graph of the residuals, which is close. There's a residuals with a variability. That's pretty good. Good enough with all that stuff. They'll give you this information. They don't want you figuring it out. Here is the y-intercept. There is the slope. Here is r squared. Here is s. You can find r. Just remember that r is negative because the slope is negative. Here's the standard error of the slope. Here's the t-score of the slope. And then there is the p-value. This r squared you never use. Again, just kind of soak all that stuff up. If you can extract all that from this, you're good. To calculate the confidence interval from this data, you're going to take, all they're going to do is for slopes, you're going to take the negative 0.16292. That's my test. That's my sample. B, plus minus, and I think they wanted 90%. 90%. So you're going to use your table or your calculator or your Desmos or your fancy program. Program, critical value, run it, its means, and it was 0.9. And there's where it says n minus 1 if means, n minus 2 if slope. And I already forgot what df was supposed to be. Keep, apply. 16 used F-150 trucks. 14. Boom. There's the t-score, 1.76. That you got to know how to do on the test. But you should have known how to do that on 10 and 11 test. So you need to know that. That is on the test. That is on the test somewhere. Slideshow. I already forgot what it was. 17 something? There it is, 1761. And then there's the standard error, which you're going to get from right there. Okay? 1.76 times 0.0309. And you can leave it like that. That's fine. You don't actually have to calculate that. If you're doing inverse t, which I had somebody do 0 hour, right? Don't forget this. Inverse t. Hit enter. I'm trying to. There it is. Inverse t. Oh, I got to hit enter again. Inverse t. Remember, 90 is the middle. 10 left over. That means there's 5 on the left-hand side. So you got to use 5 to get that same 1.76. Okay? You should know all that stuff. Hopefully that's just a reminder. Apply, slideshow. Okay, almost done. Almost done. Click, click. Your calculator will do all this stuff, but if you have to start putting a bunch of stuff in your calculator, you're doing something wrong. Maybe you have to for homework, but on the AP exam, if you have to start putting a bunch of stuff in your calculator, you're doing something wrong. No way you should ever have to put a bunch of stuff in your calculator. Uh-oh, wrong button. When you see a list of data in an exam question, wait a moment before typing the data in your calculator. Read the question through. Often, information is provided that makes it unnecessary for you to enter the data at all. This will save you valuable time on the AP Stats exam. We're getting closer to that time where I need to start talking about that. The AP Stats exam is two parts. You have a multiple choice and you have a free response. 40 questions here, 6 questions here. 90 minutes here, 90 minutes here. Everybody's fine here. Not everybody's fine here. There will be many of you that not finish the free response. So if you start typing stuff in your calculator, that's taking up time that you don't need to take up time with. Y'all okay with what I'm saying? I give you close to the right amount of time. 40 and 6, I typically give you 20 and 2. 90 minutes, and we don't quite have 90 minutes. And normally it's not 2, sometimes it's 3, but it's not a full question. So I kind of get you close. Fair enough with all that stuff, right? So start taking that into consideration. That's why I gave you 13 minutes for frappies. 13 divided by 90 gives you the 6. I know it's 15, but number 6 always takes you more time. Number 6 takes you way longer than 13 minutes. 15. Okay, test, significance tests. Significance tests. So we still have the same conditions, liner, okay, liner. You have a hoe. Beta, not B, beta, population. Typically we think it's 0. Okay, that is, beta is the slope, guys, right? Slope. We think the slope is 0. If the slope is 0, that means what? No association. And then the ha is we're trying to prove that there's a positive association or a negative association or a association. Y'all follow what I'm saying? So the ha is either a positive association, a negative association, or there is an association. And depends on which one that they want you to do. Y'all okay with it? And then you have to define what beta is. There has been a free response question where they asked you for the hypotheses of a linear regression. So, ho, beta, not B, equals, always equals, and then ha, beta, not B, and then greater than, less than, not equal to. And then they also do this as a multiple choice type thing. Your free response on the test that you guys are going to take next week will not be linear. It will be chi-squared. There'll be 2 of them. Click. We know this formula already. Same formula. The standardized test statistic is T. That is what's on the computerized print output. This T is what that T is. Your statistic is B. Your parameter is beta. And then the standard deviation is that same, oops, sorry, that should be a lowercase. Okay, again, you won't use that because this T's on your computer printout. And if it's not on the computer printout, you have this on your computer printout, and you know that that's 0, and this is on your computer printout. And so you can use this minus this and divide it by this to get that T score. And if you have the T score, you should be able to turn that into the P value. Yay. Good, good, good. Click. There it all is. Remember that DF is n minus 2 though. I promise you n minus 1 will be one of your answers. Okay? Be careful. Da 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 da. Computer printout. Slope. Residuals. Residuals. Y'all kind of okay. They give you all that information. Or I don't know where the question is. I don't see any question. Is there convincing evidence of? I don't know. There it is. Do these data provide convincing evidence of a positive linear relationship? Ho, beta equals 0. Ha, beta is greater than 0. All the conditions are met. T critical value is 3.07. Now listen to me. I forgot about this first hour. This is why I really probably deserve a D minus. This p-value right here that they put on the computer is two-tailed. That's two-tailed. This is a one-tailed test because we're trying to say positive. So if this is two-tailed and we're trying to do a one-tailed, that means that this number has been doubled and we need to cut it in half. So our p-value is 0.002. Luckily, this one, it won't matter. 0.002, you'll still reject. 0.004, you still reject. So both of them you still reject, so you're lucky in that aspect of it. Question about that. I got the T critical value right there. There's my p-value. I don't want to say most of the time. I'm going to say most every time. They're going to give you that information. One AP test, they said, but the printer smudged the p-value when it came out, and we don't know what we're supposed to do. What conclusion should we make? And so then the student had to take this number and turn it into the p-value, which you should know how to do. Okay? Then one other year, this smudged out. And so we actually had to do the slope minus 0 and divide it by that to get the t-value. Not that bad if you knew that. And then we get the t-value, we turned it into the p-value. Click, click, divided by 2 because it's 0.002. Again, I give myself about a -4 this morning. Bad. Boom. Because the p-value is low, we got to reject. There is enough evidence to say there's a positive relationship. There is convincing evidence of a positive linear relationship. Click. Your calculator will do all this stuff, but you shouldn't have to do it. If you put all your x's in L1 and all your y's in L2, you can do a ln reg t test. You can also do a ln reg t int. The test will give you the t, it'll give you the p, it'll give you the df, it'll give you a, it'll give you b, it'll give you s. I don't know if you guys remember, when we did chapter 3, this is what we did to get our s value, because they asked us the s, and I told you guys you had to go over the tests and go down and do it. I know, that's been a long, long time ago. I hope you can check the conditions for your homework. I hope you can interpret B sub 0, B sub 1, sigma, S, E, B sub 1 in context for your homework. I hope you can construct and interpret a confidence interval for the slope of B1 for the population of the true regression line. Maybe for the test, but not the condition, not the full-blown deal. Fair enough? Not the full-blown deal. I think I'll just ask you, what is the confidence interval? And then perform a test. What is your conclusion? This is Unit 9 on AP. Inference for quantitative data slopes. 2 to 5% of the AP exam. It's not much. Next year, it's 0. Here's 2 variable data. It's 5 to 7% of the AP exam. So if you want 5 to 7% and 2 to 5%, it's looking like 12%. That's at the max. Min is like 7%. Follow what I'm saying? So it's not a huge deal, but it's enough to help us bump us up. And that's what we're trying to do. We're trying to be better than the other get dudes. If you're better than the other dudes, that helps you. But it's not a huge deal. It's not enough to keep you from failing. Yes, no, somewhat, maybe. Let me give you guys something. Let me turn this off first.